As we'll see later in the talk, though, it might also be why not active learning. But that's we'll get there. So hi, everyone. My name is Vincent. I'm a machine learning engineer over at a little company called Explosion, which is the company behind Spacey and Prodigy. Spacey is very well known for being an NLP tool, and Prodigy is a data labeling tool. That's the company I work at. So I actually deal with this whole problem of how do you learn as much as you can from data, which is kind of in this active learning space. And basically what the whole premise of the problem that most of our users face is that you have this big bucket of unlabeled data, and at some point you want to get this fancy machine learning model, and by golly, it'd be great if we had some sort of trick to get there. And then when you go online and you ask the internet, like, what should you do? The internet says active learning. It's in all the textbooks even nowadays, so active learning is probably the thing you got to do. And the goal of this talk is to dive into that idea a bit more, but it's also to suggest some other ideas that might be worth considering as well that might have been overlooked. Before getting to that, let's just discuss what active learn typically means. So what I'm going to assume is that we have some sort of data set. All of that is unlabeled. But what we could do is we could maybe do some sort of a random start, maybe sample the first 100 data points or so. Let's say this is a text classification task. So like we have a sentence and then a label. And maybe for like 100 random examples, we can get like a little data set and maybe train our first model. Now, this model might not be very good, but a classification model can give us probability values. It's like when you do predict proba in scikit-learn, you get these probability-like values that sum up to 1, and some people like to interpret that as a measure of confidence. That, in turn, can be used to create a subset. The thinking is that if you pick the examples from the original data set that aren't labeled, where the model is the most uncertain, so for binary classification, the confidence is really close to 0.5, then maybe those are some examples that the model can really learn from. You could argue those are the most confusing examples, so to say. And then you've got batch 1 and 2. The first batch was made by a random start, but the second one was actually informed by the model a little bit. And that means that we can train the second version of our model. And as you can kind of maybe get a feel for it, this is something you can actually keep on repeating. So you can keep on asking the model as it sees more data, like, hey, what are you most uncertain about? And let's focus in on that. You do this for a while, you keep on doing this, and the hope is, of course, that if you do getting annotated data this way, this is going to be much better than doing just random search and sampling randomly. That's the hope. So a really good question is to say, like, all right, sounds plausible. But is this idea really perfect? Like, does it always work? Can I just follow these ideas blindly? And to answer that question, the thing that I hope people still do, is what I always do, is I just try to benchmark it. Just really do like a very simple, hey, can I confirm that the basis of this idea at least works? And one way to benchmark is to grab just a random data set from the internet, but you can also just use the make classification function inside of scikit-learn. It's not perfect or anything like that, but like it's a theoretical benchmark that anyone should be able to simulate just from scratch. So I made a data set, and then I make this chart. On the x-axis, you see the number of data batches that have been generated and annotated. On the y-axis, you see the performance of the model. And I've done this like in a couple of rounds, and like the blue lines, the blue dots, I should say, those indicate samples where active learning took place. So you can see that in this particular instance, the blue lines or dots are just a little bit higher than the orange ones in general. So you can look at this and you can kind of go, all right, kind of seems to work. Like the active learning thing is doing what it's supposed to do. But then you change the settings, then you get a chart that looks like this. And this is always fun. Like it's always fun to kind of see if you can break it, if you can break something in practice that's really robust against breaking something in theory. But it does help to at least take a step back and think about why this might be. The thing on the left seems good. The thing on the right seems bad. And maybe if we understand that, we are much better off doing active learning stuff. So this isn't a grand unifying theory of everything, but what I will just try to highlight is some settings in this setup that cause the one chart versus the other one. So again, we do the random start in the beginning. We have our first data set, we train a model, we do probas, we make a subset, we repeat this a whole bunch of times. But if you want active learning to perform worse, one thing you could do is when you call make classification, say that there are more than 2 classes. Like introduce way more classes to the problem, and apparently something about that makes it harder for the active learning thing to do something right. Another thing you can also do is you have that start data set that you start with, that first random sample. And turns out if you make that kind of small, like the first set you give the first model, if that's like a relatively small set, turns out that that's also more likely to make active learning worse. There we go. And another thing that you can also do is make the batch size really, really big. That's also something that you can do that, at least from like playing around in a notebook, seems to have an effect. Now, those are just observations, but one sort of theory you can have when looking at this is you can say, well, maybe if I have like one random start in the beginning with lots of classes, which is kind of a harder problem, then maybe the model can overfit on that. Because we are using probas from that first model to determine what to sample next. So maybe that first batch actually matters a whole lot. And maybe that's a local optima that's kind of hard to escape if you keep on sort of reinforcing what is uncertain in your feature space. Right? There's maybe some other stuff that's also happening, but at least plausibly, I hope, you can imagine that there's actually quite a few hyperparameters to this. And it's not just Vincent doing something fun in a notebook. There's actually papers about this that you can read as well. This one was particularly fun and interesting to read. The title is Practical Obstacles to Deploying Active Learning. And the authors do a couple of clever things. The paper is full of tables like the one you see over here. Basically, this is just, they try out a whole bunch of data sets and they try out a whole bunch of approaches. And if I read this correctly, the color indicates if active learning was better or if random sampling everything was better. Blue indicates that the active learning approach was better, and red indicates that just sampling randomly is way better. It's not actually way better, because the differences between active learning doing better and random doing better are like really small. But you do look at this and also kind of go, well, it's not necessarily obvious that this is all like the right color. Maybe active learning fails here in a bunch of data sets as well. And what they were also able to confirm is that all of these problems were text classification problems. They found a general pattern that it's not really certain that it helps out a lot. But then they also tried out entity recognition, which is finding substrings in a sentence, like find all the person's names, find all the organizations, find all the Python packages, like you're interested in a substring. For those problems, it actually did end up being beneficial. Somewhat marginally, like it wasn't like an earth-shattering difference or anything, but you could at least argue empirically that, yeah, a couple of percentage points they get added. So, you know, can we learn something from this? Because again, to me it's pretty clear we can't trust that active learning will fix everything, but maybe if we learn something from this, we can at least come to approaches that might be somewhat beneficial. And one dynamic that I think is pretty interesting to zoom in on is the fact that you can overfit in the beginning, and also if you have batch sizes that are very, very big, maybe you want to do that maybe in a more micro fashion instead, where sure, you have some sort of beginning, but maybe we try to learn a little bit every time instead of learning everything from a huge batch. And that kind of brings us to how you want to train machine models in the first place. Because if I think back of how people might have sampled this, we have our first data set, then we train the model. The second data set has batch 1 and 2, then we train a model. You can do that for the third item as well. But you'll notice that this actually might be expensive, because you are training a model from scratch. Because you have a new data set, you're going to call fit predict on the thing again. That's actually not a cheap operation to do. What's more, imagine that we now use the probas for this and apply those probas to the original data set, and then we sort everything. That's also kind of expensive if you think about all the operations, because you're making the same prediction over and over again. For lots of examples, you're not going to sample anyway. So let's maybe consider doing something like this. The original idea is that you train in batch. So the idea is somewhat new data set, start from scratch, train, fit, predict, proba, go. Another thing you can also do is you can say, well, I have my data set batch, like I'll call that batch 1. Then I'm going to learn a model, and I'm going to keep the weights of that model around such that when I get like a second subset, instead of retraining everything from scratch, maybe I just have a neural network that trains for like 1 or 2 epochs on that new data set. And the whole thinking here is that as people are annotating in an interface, maybe if we only have to train 1 epoch, we don't have to like shut down the server in order to retrain the system. We can kind of do it more in an online fashion. And when you do that, there's actually some fun things that you could do, right? So imagine there's like a stream of examples that come in, kind of more in the online learning setting. You can observe a data point that comes in. You can kind of pass that to the model. The model makes a prediction. And then you can kind of do 2 things. Like either the model says, well, I'm super confident about this item, or for whatever reason that it's not interesting. Then you can say, well, let's just move on to the next example then. But maybe the example, for whatever reason, is interesting, either because of confidence or whatever reason you might have. Maybe it's a rare example, right? That could also be a reason. But then you can say, OK, then that sample is going to go to the user for annotation. And then when we get that annotation, maybe in like very small batches, then we update the model, and then we get to the next example. Obviously, this is also not going to be perfect. But the thinking is that there might be some numerical aspects to doing this in batch that do get remedied when you do it this way. From my perspective, one thing that is actually kind of nice about doing it this way is that you never have to shut down an annotation server. This is something you might be able to do on a separate thread, or at least somewhat on the fly. So you never have to really shut down something in order to retrain a whole system. You can kind of do this on the fly. But still, also in this case, the first few examples are going to matter a whole lot. You can be picky in your first sample, and you can still get stuck in the local optima. Another downside of this approach is that not every algorithm can actually learn on a stream. There's a reason why scikit-learn has a fit predict API. Sometimes it's just really convenient that you're able to do this on a batch. And especially if you're doing NLP, not every library will be robust against this, if only because of the vocabulary. What do you do when you see a new word that you've never seen before? There are approaches that can deal with this. There's a lot of cool hashing stuff that you could do. But sometimes, if you're doing text classification, the vocabulary cannot really update. Like, not every library properly supports that. So even though I can argue that there are some cool things about this approach, also here, it's not like there's a free lunch. You still got to be a little bit mindful. So there's also another thing. We can take tons of unlabeled data, and we can apply active learning. We get our fancy model. But it also helps us take a small step back and think about this from like a very sort of meta-theoretical angle to see if there's like a potential for like a silent failure as well. Because there is. So, OK, how do you do ML? Well, even if we have a data set that's somewhat reasonable, that has some annotations, like binary classification or whatever, then we still think that making a train and validation set is a pretty good idea. Like, you can run your data on the train set, and you can judge the model on it, but it's kind of like cheating. We do have this consensus that having some sort of evaluation set separate from the set that actually sees the data while training is a pretty good idea. But how do you decide what goes into the validation set and what goes into the train set? I might argue, and again, there's considerations, but I might argue that you want the validation set to resemble reality as much as possible, because you're evaluating on that set. So it makes sense that you're going to go for something that really mimics reality as much as you can, even if it's not perfect. Conversely, you also want the train set to be resembling the validation set. Like, if you're going to train on something completely different than what's in your validation set, you're also going to be in a pickle. So that's why a lot of people say that you want these train sets and validation sets to be sampled independently of each other, just randomly, basically. So that feels like the most pure way to go about this. But what does active learning actually do? Well, active learning takes the model that's just been trained to determine the next data points to sample. That goes against this principle. So I showed you charts, right, where I had like a validation set, and like I would show which model performs best. But the moment you actually do this in practice, where you're really starting from scratch, you got to be careful here, because the number that you get out of your system is determined by this phenomenon. And there might be this situation where you get the impression that your metric is really good, because your validation set contains all the samples that your model is sampling right now and might not resemble reality, because active learning is not the same as sampling independently. So internet says do active learning, but I would argue here that we should also remember it's not going to be perfect. There's definitely like little snakes under the tall grass. So, OK, what if we take a step back? Mainly because always when I find myself in like a theoretical conundrum, I try to take a step back as much as possible and try to think of like all the chess pieces on the board and see if there's like a maybe bigger pattern to what we're doing. Because sometimes it's easier to dive into details, but sometimes it's actually nice to let details go and see if there's maybe more general something taking place. So I might argue that from a very high perspective, active learning is basically using a trained model to prioritize the examples that haven't been annotated yet. At a very, very high level, like forget about the proba details, but that's kind of what we're doing. We're saying we've got a bunch of stuff that's unlabeled, we have some sort of machine learning model, and we're going to try to use that model to like figure out what to do next. But what if we look at it slightly differently? What if we say, well, in the beginning, there's like not enough data to learn from, but maybe we can also look at picking the data set that we want to use and giving that particular data set to the model. Maybe that's teaching. Because you could argue like, hey model, this is the stuff I want you to look at first. Go. And it's kind of a way to steer the model, maybe. And it's something that I, as like the algorithm designer, tend to have a lot of influence on. So maybe we shouldn't look at like this one system of active learning that's like the way to get new annotation examples. Maybe we should say, well, yeah, you've got the trained model trick, but there's tons of other tricks that will also find interesting subsets for you. And maybe that's the most important thing to realize. Because if we think about it from a perspective of, hey, we are teaching a model here that also empowers you as the model, of the human, a bit more, because you get to decide what's important for this model. And active learning might be a useful trick, but it might also be nice to just see how far we can stretch our creative freedom here. And I think I have time, right? We're kind of OK on time. So what I would like to do is just show you two tricks that, in my mind, fall into this active teaching category that are kind of out there, but are also just super neat. The stuff that I found out while working at my company last year. One of them is a single label UMAP trick, and the other trick is that making mistakes can often lead to profit. So I'm going to be a bit hand-wavy here, but here's the neat trick. Let's say that you've got a set of images, and we have Hugging Face or whatever source to give us embeddings. So image goes in, numeric array comes out. Tons of different ways to do this, but we have methods for this. Probably something deep learning, machines go brr, but you get some sort of vector. And you can kind of assume that if two vectors are similar, the two images are probably also similar. Tons of ways to do this, but we have these pre-trained models. So OK, we've got this. What I could do then is instead of having an n-dimensional array, I can turn it into a two-dimensional array. You can do that with principal component analysis, PCA. My favorite trick is UMAP. There's lots of different ways to do this. But the cool thing about having a two-dimensional representation that somehow still links back to the old representation is that you can make a scatter chart. And you get these blobs, you get these clusters. But what if now, right? Given that we have systems that can do this, but what if we only sample images that have the same class? Right? So we have some sort of model, and the model says, oh, these are all the dogs. So I only sample images that are supposed to be dogs, and then I look at what the scatter chart looks like. They can kind of wonder, well, if they're all the same label, they should be all like kind of similar. So maybe I should expect a single blob to be there. And if there's not a single blob, but very clearly there are 4 blobs, let's say, what does that mean? A lot of details depend on like which embedding library you use, and like there's lots of details here. But I hope that you do feel this thing of like, hey, yeah, if the scatter chart shows very clearly distinct different clusters, that's at least worth an investigation. So I made a tool that actually is pretty good at this. And one of the users on GitHub actually showed me a really cool demo that I would like to show to you as well. So what I'm about to show you is I'm about to show you a scatter chart, as well as some images inside of that scatter chart. And hopefully you can all see this. Yes. The images that we're about to look at are from this website, Quick Draw. This is an experiment by Google where users get like text, and they got to draw that in 10 seconds. So the doodles are like not always perfect, but you can download this data, and you can say, give me all the pictures of Mona Lisa. And then what I can do is do the UMap trick. I've done it beforehand. And I can say, hey, let's open that up in bulk. It's the tool that I made. And what you can see here is that if you look at all the Mona Lisas, there's kind of like 4 clusters. So let's zoom in. Art, ain't it a beauty? OK, so but these are faces. So I can kind of go like, all right, this could be a Mona Lisa. What are the other clusters then doing? Oh, right, it's Mona Lisa in a frame. OK, I kind of get that. What are the other 2 clusters doing? Right, so this is a frame with 2 lines. All right. What's this? Oh, right, so users sometimes submit gibberish because there's not enough time to actually draw this thing. OK, let's label this. Right? This is very much, again, the human is in the loop, but this is, for me, a very good reason to prioritize a subset, because this should not be happening. I can definitely sympathize with the other clusters that I see. Like the frame, yeah, OK, that has an influence on the embeddings, sure, but this feels too distinct, and just a quick glimpse already tells me this is not the Mona Lisa. We got to relabel this. And I don't need active learning to do this, right? That's also kind of a cool way of thinking about it. Another cool thing about this trick, by the way, is that you can look at this trick as kind of like an active learning thing where we don't have a large data set just yet. But it can also be seen as like a hindsight thing for data quality. Like maybe if someone gives me a labeled data set, I should just do this exercise to make sure there's no kerfuffle in it. Because a lot of these public benchmarking data sets do have issues in them. And just the fact that we can say, well, it's supposed to be a single label, that's a good heuristic. Also, you can pip install bulk. It's useful for stuff like this. There's also other stuff that we can do, though. And that brings me to like a new project of mine. I have a website called Vincent's Archive front page. The whole point of Vincent's Archive front page is that this is a front page of the internet for me, of stuff that I'm interested in. There's a bunch of classifiers. It's deployed on GitHub pages. It's a GitHub Actions job. Every day, I scrape Archive to see if there are papers about topics that I'm interested in. One of these topics is new data sets. Sometimes people release a new data set that's just kind of interesting because it's unconventional and does something that I typically don't do. For example, there is the Chess Vision dataset. There's this 3D animation tool called Blender that has a Python API, and people use that to programmatically generate chessboards with chess pieces on it, such that they could have a dataset that can then be used to, like, whenever someone makes a photo of a chessboard, to figure out what the patterns are, so to say. This also comes with like a model. This is like, OK, this is stuff I would like to see. Like, Twitter is not what it used to be anymore. Finding these articles is nowadays kind of hard, so I made this tool. But 2 things that are cool is, one, I actually see these cool papers. But also, I built this in such a way that the classifier works on sentences. So it also is able to highlight the sentence that makes the classifier go, ooh, this is something Vincent might like. So I get this little confidence indicator over here. I get this little highlight. So this is telling me, so I can look at this and kind of go, all right, this is legit. Like, this is fine. Sometimes, though, it also doesn't do what I want. So there's a paper here called A Novel Neural Network-Based Federated Learning System for Imbalanced and Non-IID Data. Interesting topic, but it's not about a new data set. And then I look at why the model thinks this, and it's like, we evaluate our proposed systems on 5 well-known benchmark data sets, and yeah, I can kind of get where it's going wrong here. Because sometimes a benchmark data set is about a data set, but it's not new. So that's a mistake from the classifier. So maybe instead of doing active learning, how about I go to all my unlabeled examples and I just go, find me more sentences like that, because that's the thing that my model does wrong right now. Again, I don't need active learning for any of this, but I would just like to get more samples like this, just so I can push against the model believing that this is what I want. And, you know, I am a big believer in yes code tools. So if you go to the front page thing that I made, it comes with a command line app. And I can say that I want to annotate some new data. There's a couple of topics that I can pick from. I want the new dataset topic. I want to make predictions on a sentence level. I'm going to use this tool that I made that does approximate nearest neighbor lookup. I give it the sentence that I want, and then machine goes brr. And in the background, it's doing like the index lookup. It's trying to find examples like this one, where it's about a benchmark data set. And if I open this, extensive experiments on benchmark data sets demonstrate the effectiveness of our proposed method. Yeah, this is a sentence that's very similar to what I saw go wrong, but it's also a sentence I don't want to have labeled as new data set, so I can say no. A very similar sentence, I can say no. I can say no, etc. Right? But the point here is this is not active learning, this is active teaching. I am well aware of the problem that I want to solve. I want to steer the model towards behavior that I'm interested in. And maybe just thinking about this as an active learning problem, and I should think about it that way, maybe that is the biggest constraint here. And that's also kind of the point. So just to name a couple of active learning techniques that you could go ahead and use. For the first batch, you can sample randomly. But you can also do your best to just sample as wide a net as you can. Like do k-means and take those centroids. Like really make sure that you don't get stuck in a local optima. That's a technique you can do. If you're doing stuff as you go, maybe the recent stuff matters more than the old stuff, so you can try to do that. You can focus on examples where the model gets it wrong. What you can also do is have 2 different models that are both good, but when they disagree, something interesting might be happening, so sample more of those. Lots of tricks. But the main thing I hope that is cool about all of this is that when you do active teaching, when you try to teach the model the behavior that you want, you are in the loop. You're still behind the steering wheel, which also means that you yourself are learning. And maybe that's half of the beauty that we're talking about here. The use of ML here isn't just to make a prediction. It is also meant to interactively increase your own understanding. And that's, I think, a very beautiful main point. When you're trying to make models, you should really grant yourself some creative freedom here. There's definitely more than one trick, and you want a solution that fits your specific problem. So I really recommend you to think about your own teaching tactic here, and to maybe iterate from there. And maybe that's also something that we can celebrate. We don't have to stick to one trick all the time. We can also apply some natural intelligence. One more thing. So, active teaching is really cool, and we kind of need more good data sets as well. And it just so happens that I work at a company that does stuff in that domain. So you can imagine that it's very tempting to me to maybe see if we can do this collaborative thing where together we try to get this lovely annotated data set for a bunch of tasks. Not just for my own front page, but there's like a couple of, I think, community data sets that could do the community a bunch of good. So come talk to me after. I do have to, I have a kid who needs to go to bed, and I'm the only one who can manage that. So I do have to leave early. But after this talk, I'll be around here for another hour. And if any of you are interested in doing some active teaching with me, my boss actually promised me an annotation cluster. And there are some data sets that I want to annotate and make public. And I promise you, everything that we'll annotate together will become public. We can also do some cool stuff with annotator agreement when we do this. But I just want to publicly announce, I have some data sets that need annotating. And if people want to join in and learn, come talk to me, because I think there's some cool stuff that we can do. Thanks for listening. Ask me anything about these projects. And I guess the final thing that I want to say, there's a friend of mine in the audience called Tunde, and right before this talk, I couldn't really get lunch. She went to the Albert Heijn to get me an egg and cheese sandwich. So if you're all going to clap, could you please clap for her? Because that was the nicest thing. So Tunde thanks everyone else to ask me anything. I kind of want to say. Thanks. Oh, and I've got stickers, if people, you know. The stickers is always the one. Good. Hope this was useful.
Yeah, we have 5 minutes for questions. So. Yeah, these guys.
All right, thanks for the lovely talk. Have you done some experiments with the online learning part and maybe compared it to the active learning just to see what happens if you use the techniques that you described? Do you have a sense for that?
A bit. So the general underbelly feeling that I have is that active teaching, like taking a step back, thinking creative, that beats everything. So with that in mind, I've done some minor things. But I would also argue here, like the reason that I think the online thing is kind of interesting, more has to do with the fact that the process can continue because the update doesn't take so long. Like retraining a model from scratch and sorting the empty, no annotation, that's just the bottleneck. So the main thing that the online learning provides is just that. Again, think more about your own problem. I think that's the more useful thing to do. And zooming in too much on active learning can also be a distraction. That's kind of my main lesson.
Thank you.
Could still be some cool benchmarks, though. So if anyone has tried stuff, like, do tell me. Like, I would be interested.
Next question.
Wasn't you also?
Yeah. So at the end, you mentioned like the measuring disagreement between models.
Yeah.
Do you think the new foundational models like segment anything are valuable in there?
If only someone wrote a blog post about that. Large disagreement modeling. Yeah, that sounds like an interesting blog post. So this is definitely a pretty awesome thing. So on the Spacey side of things, we've got 2 people on the Spacey LLM team now. So we've made a Spacey plugin where you can basically give us your labels, give a description of the label, give us a couple of examples that the LLM did wrong before. We will then configure the LLM that you like. We integrate with a whole bunch of backends. That model can then be compared against your own local Spacey model. And we also have annotation recipes that help you figure out, hey, when do they disagree, so you can annotate those first. And I will definitely say, I think that's the coolest LLM trick so far, because the LLM, if you're doing stuff with text, the LLM will kind of guarantee, although it's not cheap, maybe, but it will kind of guarantee that you always have a second model. So you can always do this trick. And the cool thing as well is that when you do differences between models, you also don't want the 2 models to be almost the same. Like, it's kind of like saying, oh, I've tried a random forest and XGBoost, and when they disagree, I'm going to do something, but they're kind of the same. Here, I could argue that the way that Spacey might go about it, if you have like a convolutional model with vectors, is quite a bit different to the way that the LLM would deal with it. So when they disagree, that's probably interesting. Either I'm going to expose myself to examples that improves the prompt, or I'm going to have examples that will improve the model, which is also good. The blog post has fancy diagrams. But this is like, yeah, the model disagreement with LLMs is a legit use case, I think, especially with the advent of more and more of these models being local on your disk and also the ability to fine-tune. And there's still like a lot of work to do in that domain, of course, but just the fact that this is available as a starting out trick, I've found that to be pretty good, especially if you're dealing with named entities. Because this usually involves a whole lot of clicking around. And just having models that can do this for you usually makes it a lot quicker to annotate data as well. But yeah, that LLM stuff in this domain, I think, is a pretty legit use case, also because there's a human in the loop. And we've got some pretty good results here. Yeah.
Thanks.
I should say about that one thing about this, though. In the beginning, the LLM performs better than the Spacey model we found. But there's something about the threshold of 2,000 examples or so, where usually the Spacey model actually performs a bit better. My theory there, and this depends on the data set, this is not like a whole encompassing saying, but one thing I can imagine is that the LLM is really supposed to be a super general thing, and your model is usually supposed to be a very specific thing. So that does help explain that in the beginning the LLM might be better, but the moment you reach a threshold of a couple thousand data points, the local Spacey model can actually perform a lot better as well. Something to keep in mind. Like LLM is not always better.
Okay. Thanks. We have time for one last question. Anyone in the back has a question? No?
And there's also someone at the front here.
Please pass on the mic.
Okay, good catch. Yeah, I was thinking about that, about dataset size.
Yep.
Because like the fact is that we have tons of unlabeled data, and we always think that the solution is, okay, let's find an algorithm that can allow us to use all the dataset. But from what I was seeing from your example, your last example about the tool, sometimes it's more about having a few examples about good labels. And can you elaborate about saturation of performance with the dataset size?
So, I guess like an extreme example here, right? Is say, I've got one image of a dog, I've got one image of a cat, I can rotate them slightly, boom, I've got thousands of examples. Okay, on paper, I've got thousands of examples. Is that really going to lead me to a good model? Maybe not. Maybe the data set also needs some diversity. So one way to think about it is you want to have a data set that's specific enough to your use case such that you don't apply lessons you don't need, but you still need enough diversity. And does like the number of examples capture that, or should you just make sure that you've got like a couple of distinct clusters? Like that's also another way of thinking about it, at least. And again, when I apply this trick where I just look at what kind of mistakes does it make, usually it's not like all these mistakes are from one cluster, so to say. There's actually like a kind of a wide variety of mistakes that it makes. So again, natural intelligence. Like think about the problem, iterate, try to understand why certain mistakes are more prevalent than others, and just repeat. Maybe that's better than hoping an algorithm will solve it.
Yeah. Thanks. So
natural intelligence is all you need. It's maybe like a good statement too.
So I would like to thank Vincent for coming here for this amazing talk and introducing us to active learning. Please reach out to him.
Active teaching.
Active teaching, yes. Not learning, teaching. So I hope everyone got something out of this talk and applied to their own fields. For more information, please feel free to reach out to Vincent and also check out his LinkedIn page. Please give him a huge round of applause before leaving.